Okay, here we've got a hypothesis test. We're going to be doing a Mann Whitney test. Okay, and what we're testing for is whether the fertilizers that supply potassium increase the size of oranges. Okay, and the alternative kind of fertilizer is non-potassium fertilizer. So in terms of my hypotheses, H0 is always that no interesting difference is taking place. So I just have to get across the idea of no difference and put it in the context of oranges and fertilizers. Okay. For the alternate hypothesis, I need to look carefully at whether it's a one or two tail test. Now, what I'm testing for is an increase in the size of oranges. So therefore, the alternative isn't just that there's some difference, it has to be an increase. So here is one way that could be worded. I've got in the idea of larger sizes and I've put all the necessary context in there. Great, so on to the fun bit. Let's work out a test statistic. So I've now got the data. So I've got two groups, and what I've got to do is rank all of these data. So for Mann Whitney, we treat the two independent samples. We consider it as just one set of values for the purposes of ranking. And they've been kind. They've put the values in each sample in order. So I'm going to start ranking from 6.5. That's the smallest value. That gets a rank of 1. And then my next smallest is 6.8. So that's 2, 6.9, 7.04, 7.0 again. Oh, right. So that should have been rank 4 and 5 used for these. So that's a tied rank of 4.5 in the middle of 4.4 and 5. And then I'm on to rank 6, and that's going to be the 7.3. And rank 7 is going to be the 7.4. And rank 8 is going to be the 7.5. And then for rank 9, I've got another tied rank, 9 and 10. So that's a tied rank of 9.5 are going to be here. 9.5 again here, and then rank 11 is the 8.3, and rank 12. So I've ranked all the data. I've made appropriate use of tied ranks. Now I've got to total the ranks for either of the groups. In fact, we can do it for both. Mann Whitney always gives us two possible test statistics, U and U dashed. We can do the conversion later, but I'm actually going to work out both totals of ranks to show you how this works. So for the top group, I have to do W. Okay, and I have to do 1 plus 2 plus 6 plus 7 plus 9.5 plus 9.5 plus 12. And if I add all of those together, then my calculator gives me an answer of 47. Whereas if I sum the other ranks here, 3 plus 4.5 plus 4.5 plus 8 plus 11, we get a W value of 31. And I can take either of these W values and convert it into my test statistic U. So here's my formula for U, and of course this is given in the formula book. Okay, so I could do this with either of the values I got earlier. So if I do the first one, I could do the 47 minus, now the value of M is the number of items in that that sample that we're totaling. So we had 12 values altogether, but there were, I think, 7. Yes, here they are, 7 values in this particular subgroup that led to the W value of 47. So with M equaling 7, I can do 7 times 8 divided by 2 here and take that away from 47. So I get a U test statistic of 19, all well and good, but there's always a U dash to go with this U. Now, one way to get the U dashed is to start all over again with the same formula. Okay, U equals W minus M, M plus 1 over 2. Okay, but I'm going to work out U dash because I'm deliberately going to swap to the other W. Now the other W we found was 31, but that was based on the sample of size 5, so I have to take away 5 times 6 over 2. So I'm going to get 31, so U dash is going to equal 31 minus, this is 15, which gives me a value of 16. Okay, so I've got a U equals 19 and a U dashed value is 16. Okay, so I've gone a slightly long way around, but at least I can see that I've got two different test statistics generated from the two different groups. Now, what these numbers are telling me is that this 19 is telling me that the ranks for this group, the group with 7 observations in it, are tending to be a little bit higher than this other group. Okay, so that means these oranges, okay, tended to have the higher rankings. So therefore, these are going to have the higher diameters, they're going to have the bigger sizes compared with these oranges, okay? Now, because this is a one-tailed test, all right, I always should do a reality check at this stage. So should the first group of oranges, okay, tend to have bigger sizes than the second group of oranges? Because that's what these data are telling me. So am I happy that this group of data, the 7 item set, tend to have slightly higher values than the other set? Well, that is what my alternative hypothesis is claiming. So I don't know if this is a significant difference yet, but at least the difference that I've spotted is in the correct direction. So I can go ahead and complete the test knowing that any significance is actually genuine, in the sense that it's pointing in the direction that H1 needs it to point to draw that conclusion. Now, I mentioned I'd gone a slightly long way round. In practice, it's not strictly necessary to compute U and U dash, both of them from scratch, because, again in the formula book, there's another formula that tells us a quick way to get the U dash once we've got our U. Okay, so I could have got either of these first. Here's how we would have got the second one. The formula in the formula book is that U dashed equals Mn minus U. So in this particular case, okay, M and N are the 2 sample sizes. So for this formula here, I was using an M of 7. So I'm going to do 7 times N is the other sample size, which was 5. And if I take away U from that, I'm going to be doing 35, take away 19, take away, that should be, not equals, take away 19, and lo and behold, that equals 16. So this is the quick way to get U dashed. However, if you do both of these methods, and you get the 16 appearing in both methods, then you know you've done it right. So it's quite a useful check. Okay, now I'm ready to complete the test. So I've got a U and a U dashed. I need to select the appropriate one. So I'm going to be getting a critical value. At the point where you get a critical value, we should always have a diagram. Okay, so there's some sort of shape of the distribution. Now the table for Mann Whitney, just as with the table for the Wilcoxon signed rank test, the table you're given only will give you low values. It only gives you the lower tail. So on a 2-tailed test, this upper tail is there, but you don't look at it. Here we're just interested in looking at one tail. Okay, I know that the test statistics are the right way round, so I need to compare the relevant one with the tail that I can look up. So I've got a choice of 19 and 16, but the only one that's got a chance of being in this tail is the smaller one. So what that means is with a U and a U dashed, we always choose the smaller of these values and compare with the critical value. Okay, so I need to look this thing up here in the table. So this is the table I need. It says Mann Whitney at the top, so this is correct. And I need to find my values of M and N in this table. So going back to my work, we've got an M of 7 and an N of 5, or it could be the other way around. Okay, so they always give the smaller value first here. So 5 and 7 I should say. Okay. We've got 5s here, 5 and 7. So I've got this row of the table, and I've got a one-tailed test, and the significance level I was given back in the question was 5%. So with a 5% significance level on a one-tailed test with 5 and 7, this value is 6. So my critical value of my test statistic is 6. Okay. If I ever actually achieve that value spot on, then that does count as being significant. But if I look at my test statistic of 16, then it's not even close. 16 is clearly greater than 6, but this big white bit is the not significant region, so this is clearly not significant at the 5% level, and therefore I'm going to be accepting the null hypothesis H0. Okay, so I've done my comparison, I've made my decision. Now I need to state my conclusion in context. Because I'm accepting H0, and this is what some of the model answers you may have get wrong, whenever we're accepting H0, we say no evidence. Okay, when we're rejecting H0, that's because we've got evidence to do it. So we say no evidence, and we should say at the 5% level. to conclude, and now I have to go back and make sure I've put this in context. So referring back to the alternate hypothesis, I was testing whether there would be larger sizes of the oranges treated with the potassium fertilizer. Well, I've not got evidence for that, so I'm going to write no evidence at the 5% level to conclude that the oranges treated with the fertilizer had larger sizes than the others. So I've given a clear conclusion in context, and that completes this question.